Hi, everybody. So now we're going to talk about these factor groups that I've been alluding to. And I think the best way to get into this is to look at the definition and then see if we can make sense out of it. So here we go. Suppose we have a group and we have a normal subgroup H. Then I'm going to introduce this notation G mod H. That's the way you read that, G mod H. And G mod H is, as a set, it's the set of left cosets of H and G. So this is something that we've been looking at quite a bit. But what's new here is that we're going to introduce some multiplication on cosets. And the way we're going to do it is by kind of the simplest approach, namely if you have the coset AH and the coset BH, then the product of those two cosets is ABH. And so just maybe to make this completely concrete, if our group G is S3 and our normal subgroup H is the group of rotations, and then the cosets G mod H consist of the identity coset and the coset SH, the left cosets. And remember here that the number of elements in G mod H is the number of elements in G divided by the number of elements in H. This is Lagrange's theorem. Of course, that could be infinite, in which case it's just infinite. But if G is a finite group, or if G is a infinite group and H is a subgroup of finite index, then this could be a finite number. And so the multiplication, this is just two elements. And the multiplication here would be that H times H is H. I mean, we can think of H, for example, as EH. And so EH times EH is EH. And then we would have SH times SH is S squared H, which is just EH again. And then EH times SH is SH, but that's also SH times EH. So G mod H has the multiplication table EH, SH, EH, SH, EH, EH, SH, SH. So it looks like a copy of Z mod 2, at least if any of this makes sense at all. The important thing to remember here is that G mod H is going to turn out to be a group, but the elements of that group are cosets, which are themselves sets. So that might take a little bit of getting used to. So the proposition, and it's one of the most important propositions in group theory, is that if G is a group and H is a normal subgroup, then this operation on cosets is well defined, and with it, the set of cosets, G mod H, becomes a group where the identity element is H, which is the same coset as EH. And if AH is a coset, its inverse is A inverse H. Now, if this multiplication makes sense at all, these 2 points are clear, because AH times EH is EH times AH, which is EAH, which is AH. So EH acts like an identity element. And AH times A inverse H is EH. And so A inverse H looks like an inverse. So those properties sort of follow immediately from this definition. But this business about being well defined is where the catch really comes in, because remember that these cosets are not single things, they're sets of things. And for example, let's look at the coset H itself. Well, it's certainly true that H is equal to EH, but it's also equal to HH for any H in H. Remember that two cosets are the same if and only if X is some multiple of Y by H on the right, or equivalently, if they intersect each other. So one coset has lots of names. And if we're going to make sense out of this multiplication, it has to make sense no matter what name we give it. So to go back to my earlier example, just using G equals S3 and H being the group of rotations, I was talking about SH as being one of the cosets, but I could instead have used RSH because these two cosets are the same. And the way to see that is, well, the easiest way maybe is to show that they have an element in common. And what's the element that they have in common? Well, RS is SR inverse. And R inverse is in H, so SR inverse is in SH. So RS is in SH, but it's certainly in RSH because H contains the identity. So these two cosets include the subset which just consists of RS. They have that element in common, and so therefore they have to be equal. But if that's true, then that would mean that if I did SH times RSH, what do I get? I get SRSH. But on the other hand, if RSH equals SH, then SH times RSH had better be equal to SH times SH, which is S squared H, which is H. So I need to know that SRSH equals H. And as it happens, it does, because I know that SRS is R inverse. So this is the same as R inverse H, but R inverse is in H, so that's equal to H. But if we had to go through this every time, we would go crazy. And so now we're going to really see where the hypothesis that H is normal comes in. Because here's what this all boils down to. We have to show, so suppose we have AH is equal to BH, and CH is equal to DH. So these are different names for the same coset. Well, then by definition, AH times CH is equal to ACH. But we hope that this is equal to BDH. And if it is, then that means that we can use any name that we want for the cosets. And if it isn't, then we're in trouble. So if we want ACH to equal BDH, how can we check that out? Well, we have to use these facts here. So the fact that AH equals BH means that A is B times some element of H. Let's call it H1. And the fact that CH equals DH means C is equal to D H2, where here H1 and H2 are in H. So that means that AC big H is equal to, well, A is BH1 and C is DH2H. And H2H, this is just H again, because if you multiply H by an element of H, you get the same coset. So this is BH1DH. And now we're sort of in trouble, at least at first glance, because this H here is kind of in the way, and we don't want it there. But remember that H is a normal subgroup. So that means that DH is the same as HD. In other words, we can move D past the subgroup H and keep the same coset. And now we're in good shape because we have BH1HD And H1H is just H, because again, little h is in big H. So this is big B big HD, and now we can use the normality again. This HD is again equal to DH, so we get BDH, since HD equals DH. Let me write that down here. HD equals DH, since H is normal. And so you see that if we had, instead of using the names A and C H for our cosets, we had used the names B and D for our cosets, we would end up with two answers, ACH and BDH, and we might think, oh, those are different. But in fact, those are actually the same as sets. ACH and BDH are really the same coset. And that means that this group law that we've defined makes sense. If H were not normal, this wouldn't work. What would happen is that when we did ACH, we'd get one answer. But when we did BDH, we would get a different coset. And so it can't be the case that if A equals B and C equals D, you better have AC equals BD or there's a problem, and that would go wrong. And so it's the normal hypothesis which exactly fixes that problem. Okay, let's look at some examples. Well, one example is something that we have seen many times before, going back to Math 2710, but now we have new language to talk about it. So let's let G be the group of integers, and H be the subgroup of G, which consists of multiples of a number n. And let's assume here that, just for the sake of making this not trivial, that n is bigger than 1. So H is a subgroup, and remember that since G is abelian, H is normal. Every subgroup of an abelian subgroup is normal. The cosets of H are of the form A plus NZ for A between 0 and n minus 1. We worked this out back in the section on cosets. The point is that these things are A plus NZ intersect A prime plus NZ is the empty set if A is not congruent to A prime mod n. In other words, if these don't, these are the numbers which have remainder A when divided by n. These are the numbers which have remainder A prime when divided by n. Those two sets are completely disjoint if the remainders are different. That's the division algorithm. So this goes way back. And they're equal if A is congruent to A prime mod n. So we have n cosets. It has n cosets. And they consist of nz, 1 plus nz, out to n minus 1 plus nz. And the group law is that you add A plus nz plus B plus nz is A plus B plus nz. And for example, if n were, let's say, 7, and we looked at 5 plus nz plus 6 plus nz, I would get, n is 7, I would get 11 plus nz. But 11 plus nz, this is 11 plus 7z. These are everything which is 11 more than a multiple of 7. That's exactly the same set of elements as everything which is 4 more than a multiple of 7. These two cosets are the same. And that, so we would have that 5 plus 7z plus 6 plus 7z is 4 plus 7z. And more generally, we would have that A plus nz plus B plus nz is A plus B plus nz, where A plus B is congruent to A plus B mod n. In other words, this is a fancy way, a group theoretic way, using factor groups to construct the group we already know of as Zn, whose elements were the congruence classes. The cosets are the congruence classes, and the addition of congruence classes is the addition of cosets. And if you go way back, you will see that this check on whether this is well defined, we did that. That was the question of if I was writing, let's say, A as A plus NZ and B as B plus NZ, and then I had C is C plus NZ and D is D plus NZ, and A and C are the same if and only if A is congruent to C mod n, and B is equal to D, the congruence classes, if and only if B is congruent to D mod n. And so when you add them, A plus C is equal to B plus D, because if A is congruent to C mod n and B is congruent to D mod n, then A plus B is congruent to C plus D mod n. So you can think of this quotient group construction as a very big generalization of what we did with the integers mod n. Let's look at another example, but again working with the integers. Suppose instead we started with G is Zn. Again, I'm going to assume n is bigger than or equal to 2. And suppose that D is a divisor of n. So the cyclic subgroup generated by D, which contains sort of, I guess, 0, D, 2D, and so forth. Another way to think about that is it's DZN. Because it's the multiples of, if I take 0, 1 up to n minus 1, which are the elements of the congruence classes for Z mod n, I multiply them all by D, I'm going to get D, 2D, 3D, 4D, and so forth up to n minus 1D, and then I'm going to get ND, which is 0, n plus 1D, and so on, which is D, 2D. So it's a different notation for what we were calling the cyclic subgroup generated by D. And now let's ask, what is Z mod H? So, G mod H. Let's look at an example. If G were Z6 and D were 2, then the cyclic subgroup generated by 2 is the set 0, 2, 4, and then 6, which is the same thing again. So the cosets, so this is a group of order 6. This is a group of order 3. So the coset, there are two cosets, and what are they? Well, the cosets are D itself. That's always a coset, H if you like. And then there's 1 plus H, or 1 plus the multiples of D. And if you think of that as a coset, it's 1, 3, 5. But that's it. There is supposed to be two cosets, and we found them. And what is the group law? Well, it's a group with two elements, so we know it very well. It's the only group with two elements. And what we see here is that the subgroup D is a copy of Z3 because it's a 3-element cyclic subgroup, 0, 2, 4. And it's a subgroup of Z6, and the quotient of Z6 by the subgroup generated by D is a 2-element subgroup, which is isomorphic to Z2. So more generally, if we have Z, which is Zn, and D, which is 0, D, 2D, and so forth, up to n over D minus 1 D, which is ND minus D. And then the next one would be ND, which takes me back to the beginning, 0. this is our subgroup of order with n over d elements. So the quotient group G mod the subgroup generated by D must have D elements. And what are the cosets? Well, they fill in sort of the gap between 0 and D here. Namely, they consist of D itself, 1 plus D, all the way out to D minus 1 plus D. Because what happens after that? Well, here are, first of all, let's notice that there are, how many here? There are D cosets. They're all different because this one contains 0. This one doesn't contain 0, but it contains 1, and so on. The next one contains 2, and the last one contains D minus 1. So they are all different. And there's D of them, so that must be all of them. And what's the group law? Well, the group law is when you add I plus D to J plus D, you get I plus J plus D. And the best way to think about this is now instead of doing addition mod N, you're doing addition mod D, because you're taking I plus J. These are elements of Z and Zn, but if you get a multiple of D, then you're in this coset, and so you become it effectively 0. And so what you end up getting from this is that if you take Zn mod out by the subgroup generated by D, you get the cyclic group with D elements. And this subgroup here has N over D elements. So in this way, we get relationships between the different ZMs. Basically, if you look at Z20 and you mod out by the cyclic subgroup generated by 5, you get Z5. And what's going on here is that the cosets are 5, 1 plus 5, 2 plus 5, 3 plus 5, and 4 plus 5. And the addition is you add, but anytime you get a multiple of 5, you kind of throw it away. So effectively, you're doing arithmetic mod 5 on these cosets. Let's do one more example of factor groups. So we're the non-abelian group now. So this is one of our very common cases. So G has two n elements. H has n elements. It's the subgroup of rotations. So G mod H has 2 elements. And of course, there's only one group of order 2, so we know what it is. What are the 2 cosets? Well, we worked this out before. One coset is H, which consists of the rotations. And the other coset is SH, which are the rotations times reflections. And H times H is H. H times SH is SH times H is SH. And SH times SH is H. So it's our old friend, the group with 2 elements. There are lots more interesting examples, and we will talk about those in another video.